Right. I'll make you host again. All right. Cool.
Okay. Is my screen visible?
Yeah.
Okay, I think we can get started. Okay, hey all, welcome to the April community call. My name is Bhavani Sudha. I'm a PMC member of the Apache Hudi project. Today we have two interesting talks. One is a presentation from Halodoc by Jitendra Shah, and the other one is a demo from Vinoth Govindarajan. I'll give a short community update and then hand over to the speakers. And then finally, we can open floor for questions. So here are a few insights from last month. This is taken from Pulse in the GitHub insights. So we have 252 active pull requests. We merged 178 pull requests over the last month. We have closed 26 issues and we have 45 new issues. We have about 49 authors. We passed the 1,900 Slack users, and we have 4 new RFCs if you're interested. I've attached the link here. Some of them, to briefly talk about them, we have one RFC introducing secondary index based on the Zine to improve query performance. And we have another RFC for improving timeline server to consolidate all access to timelines through the embedded timeline server. And then the other RFC is about making writes efficient using log-free message queues. And then the last one is a change data capture, which gives pre-post images along with change type, etc., on all the incremental queries, much like how full change data capture model work. So these are some interesting RFCs we have. Please take a look at the links and please provide feedback. That'd be great. So if you're looking for ways to engage with our community, these are different opportunities that you can engage with our community. And we also have office hours every Thursday, 8 a.m. to 8:30 a.m. PST. Awesome. So thanks for the awesome contributions, and I'll quickly hand over to Jitendra to talk us through the journey.
Okay, so yeah, hope I'm audible, right?
Yes.
Okay, so thanks, Sudha. I think I'll just give you a walkthrough of like what our data platform journey looks like, right? So, and also like how we are basically leveraging Apache Hudi to build the Lakehouse architecture. So before I start, let me introduce myself. So again, I'm Jitendra Shah. So I'm a senior data engineer at Halodoc, working to build a data platform over here. So my past experience holds building a streaming and BAS data pipeline. So, okay, hoping that I'll just try to set up a content of this session. So next slide, please. Okay, so we'll try to cover two things today, right? So one, as a Halodoc, what we are basically and what we do as a services. And second, we'll try to talk about the data platform journey, right? So what our early days data platform looks like, what are the challenges we had, and basically why there was a need for building a platform 2.0. Next. Okay, so Halodoc is basically a healthcare startup in Indonesia. So that has a vision to simplify access to healthcare across the Indonesian citizens. So we have multiple apps integrated with our products, so Android, iOS, and the web. So we do have monthly active users, like currently you can see the number as 18 million and all. So we are in a focus to basically provide easy access to healthcare to everyone using the tech and the app. Okay, so let's talk about some of the services what we provide, right? So on a high level, right, these are the top services what we provide. So first one is a chat with the doctor. So it means the teleconsultations. Someone can teleconsult with the doctor and basically identify or basically get some consultations from the doctor. Second, we have a health store, right? So this is basically buying medicines from the store. So we can easily buy a medicine from the online storage and basically get the medicines over the home. Third one is the appointment booking. So we can do an appointment booking from the app and visit the hospital and without waiting for the queue at the hospitals, right? Similarly, we have lab test, link insurance, and articles. So these are again the high level services. We do have some additional microservice, I think, related to COVID. So some of them can be a COVID vaccination drive, or it can be a PCR drive-through and all those, right? So these are the high-level services what we provide in our platform. Next. Okay, let me talk about the platform 1.0 architecture, right? Before I try to talk about the architecture, let me give you a very quick demo, like how our data looks like and basically what are the data we capture, right? So as a user, right, if I come to the Halodoc app, what I do is I log into the app and basically go for multiple pages and looks for all the products or the services what we have, right? So these are the events what we basically captured in our clickstream tool, and those are nothing but a NoSQL database, right? Once I make some kind of a transactions, right, so these transactions are basically captured in the relational database. So those are being backed by the MySQL or the Postgres database. Once all these transactions are completed, right, there will be some finance reconciliation that is happening from the finance team, either daily, weekly, or a monthly basis. So that is in some kind of flat files it will be sitting on. So if I have to look on the data points, right, we have variety of data sources sitting in NoSQL, RDBMS, and also flat files, right? So how we build our platform 1.0 was to bring all this data into a single source so that anyone can have access to this and perform the analytics on top of that, right? So in the early days, what do we use, like Apache Airflow for orchestration and also bringing the data into S3. So S3 acts as a landing zone since we leverage the AWS cloud, and data will be moved into Redshift without any, again, modification. So mostly this was moved to basically perform the offset operation, right? Because the mutable data set cannot be performed within the S3 without any other external basically framework, right? So pretty much very simple architectures which serves us for 1 year, 2 year down the line. But there was a key challenges with this platform, right? So that was like a Redshift for analytical and the reporting use case. So that means all the data from various sources was landing into one zone, and it was very hard to scale that independently. Like if you have a storage increment, you have to go and pay for the compute also, right? That is one of the challenge. Second, we were also building the real-time platform separately to basically serve the streaming data use case, right? And that was an overhead in maintenance, like two platform building independently. Third, we were using Airflow for ETL. So that means a data was transferring from the Airflow memory. So we were needing a very big instance of the Airflow, like whenever there is a high spike in the data. Fourth, there was no proper dimensional modeling followed in the data warehouse. So the use case, let's say the user brings us the use case, we understand the business logic, we applied it, and basically creates a data mart and hand over to them. So this created a lot of data silos, like sitting multiple places and not having a centralized store where we can maintain and basically give information to the users, like this is what has been done. Fifth, looking in the COVID time, right? I mean, in last 2 years, the data consumptions in our platform, right, has increased a lot. I mean, there has been a lot of analytics that need to be performed because of this change. So these were the very high level key challenges we have identified in the platform 1.0. Okay, so what next, right? So I think generally everyone has two options, right? Either you optimize or enhance the existing system basically to meet the emerging needs, or you build a modern data platform 2.0 parallelly, right? So each has a pros and cons. So we went with the second approach. The reason behind that is it was not that easy to integrate new features in the existing platform since the architectures were very different. It was very hard to work parallelly. I mean, modifying the existing system and making the system stable also. So the second approach, how it helps us is we were independently able to build a platform 2.0 parallelly and basically migrate one pipeline or one data source at a time. So that saves a lot of time, though the cost was high at the beginning, but we thought on the longer term. So in the longer term, the cost will be less. Yeah. So I think again, we did a groundwork, right? So before we start our platform 2.0 building, so we identified few considerations like, or the capabilities that platform 2.0 should support. One, single truth of data across the organization. We wanted to democratize the data access to our Halodoc users, so that they can easily access the data. Second, we wanted to enable analytics a little faster. I mean, if there is a new service, let's say COVID was there, right? The new service that has added. So bringing the data into an analytical platform should be faster so that analytical can be done. Third, it should store all kinds of data. At the beginning, I mentioned like we have structures, semi-structures, and we do have unstructured data also. So platforms should be capable of storing all kinds of data. Lastly, platforms should be able to perform mutable and immutable data sets, right? So it should basically replicate the source behavior. So there was two kinds of a source. One, a data that is changing over a period of time. Second, data is not changing, right? So we wanted to build a system which can support both the use case. So this was the high level capability what we wanted to build in our system. Okay, so again, platform 2.0 architecture, right, looks like this. So what we did is multiple data source we have. So we introduce change data captures instead of doing a batch kind of a migration. Our main goal was to bring all the source data into an ingestion tier that is act as a raw zone with the help of change data capture, and we leverage AWS data migration service for this. We also have a control plane. So control plane is nothing but a microservice kind of architecture, which is responsible for metadata repository and also the pipeline execution. That means any pipeline can be controlled with the help of a control plane. And each metadata or the job executions, failure status, everything will be captured on the metadata. So everything can act as a central repository. So if anything we want to do tomorrow, right, we can just go on the control plane and look the behavior or the status of the pipelines. Right. So Lambda was introduced to track each file events that has been dropped on the S3 and track in the control plane. So tomorrow, if something, some error has happened, we can easily debug or we can easily do a backfill of the data set. Right. So Apache Hudi comes in play when we wanted to basically create a mutable transactional data lake. Right. So we introduced Apache Hudi with EMR for processing the data from the raw zone and storing back into the S3 as analytics type. So analytical tier act as a lakehouse architecture for us. And we basically store all the metadata in the Glue data catalog, and Athena was being introduced to query the data catalog. So on a high level, this was the lakehouse architecture, right? So we also introduced the data warehouse because most of our previous reporting or the dashboarding was done on the Redshift. And if we directly move everything on the S3, it was quite difficult for us to manage. So that's where we introduced Redshift. So all the data that is needed for the reporting use case has been migrated to Redshift by following a proper schema modeling. So we introduced here star schema modeling and have the data in terms of dimensions and the fact, and created a reporting table on top of that. Right? So if I have to look on a high level, right, there are multiple components involved in the platform, and we try to divide this platform into multiple layers, one from the ingestion layer to processing layer to transformation layer. So this gives us the flexibility for us to introduce any kind of a change or onboarding any data sets quite easy. Everything can be done from the control plane. It is a config driven kind of a pipeline. Yeah. So what we solve, right, in the new platform. So first thing is low data latency, right? In our previous architectures, I was mentioning about the batch. Like in the new architecture, since our data was being migrated with the help of change data capture, so we were able to bring the data in the lakehouse in low data latency. So if I have to talk about the time, it is like 15 minutes interval we were able to provide. Second, scalable distributed platform, right? So Apache Hudi being the open file formats, we were able to scale the storage or the compute whenever we need. Third, easy to maintain and onboard new data sources. So everything was configurable in the new platform. So if I have to bring, let's say 100 MySQL database, right? Someone has to just input in the control plane, and the pipeline would be already there, which can just identify new data source that has been added and start the migration. Fourth, next generation data platform to support future integration. So we are also looking to integrate data quality, data governance, and data lineage in our system, right? So data quality basically to identify the failure in the data, the issue or the bug in the data before our end users report us. Data governance, since we are in the healthcare domain, so that is very critical for us, like governing what data, what users have what data access, and providing security to our data set. Last, data lineage, to understand the series of transformations, what has been done over a period of time, right? So might be at the beginning, it is not critical, but down the line, if we have a lot of transformation being done, it's going to be very critical for us. So these are the features which we are able to basically integrate in the new platform independently. Okay, so this is where why we choose Apache Hudi, right? I mean, everyone knows about Apache Hudi, so just trying to tell again. So I think it gives us flexibility to decouple storage and compute. It helps to store both structured and semi-structured data set. It helps us to basically build a open file, open lakehouse, so that it can act as a single source of data across the organization. It also provides ability to store and query mutable as well as immutable data set. And it has easy integrations with multiple distributed processing engines like Spark, Hive, and many more. Yeah, so key learnings, right? I think this would be very interesting to talk, right? So I'll talk what our journey has been with Apache Hudi, right? And we identified like some of our learnings using the Apache Hudi. So first one is performing the incremental offsets in Lakehouse. So it's very easy to perform the incremental offsets in Lakehouse when you have a primary key and some particular column which can tell you like which is the latest record, right? But since our source was a MySQL database, it holds the timestamp in a second format. And that's where it becomes very challenging when you have a very frequent update that is happening on the source. So it's very hard to track in the CDC based approach also, which record is basically a latest record. So for this, we leverage a data migration service, the DMS, that helps us to add an incremental sequence on every transactional log so that we can have a offset operations in the Lakehouse. So this is one. Second is small files problem, right? So I think every time whoever builds a data lake, I think that's a very common challenge everyone face. Like you have a lot of small file and your processing or the querying takes a lot of time since it has to store a lot of metadata of the file and perform some kind of a computations. So Apache Hudi, I think again brings out of the box these features, like where it can have synchronous and asynchronous compaction over a period of time. Third, maintaining the storage size for cost reduction, right? So these also again, Apache Hudi provides multiple views of the data, right? If you are updating, you can basically have a point in time kind of a travel, but that does not require for every data set what we have, right? So that is where we can easily configure this so that storage also can be maintained. I mean, the number of commits, how much to retain within your storage. Fourth is the choosing the right storage type based on latency and business use case. This is, I think, good, like where you can identify whether you need a read optimized table or a write optimized table. So based on that, we can easily choose the Apache Hudi. For us, I think the driving factor was whoever needs a real-time data, we went with the MOR kind of a data set, and whoever are okay for data latency, which is more than 30 minutes or 1 hour, we went with the COW, copy and write. Fifth is file listing a heavy process that I think similar to second one. And the last one is the choosing the right index for Hudi data set, right? So again, it has multiple indexing concepts, so one has to choose correctly. So I think there was definitely a learning curve for us to understand all the configurations that is available on the Apache Hudi, but we were able to do, and we have shared some of our learnings in the blog. Might be, if interested, you can just go through and get in detail. Okay, this again, we also have a talk that we are going to present, like how we implemented Lakehouse architectures using Apache Hudi on Amazon EMR and Amazon Redshift. So in the Asean Summit, right, we have a deep dive on the architectures. I think today I just gave a high level, so we'll go more deeper on each layers, like how we have implemented. Implementation strategy, like a control plane, what is the concepts of control plane, how we have basically derived with that, and all those. Thirdly, features implementation. What are the features the platform supports, and the roadmap, right? So what is our visions on the data platform building? So if people are interested, they can register and basically watch this session. I would definitely say it is going to be a very useful for all of us. Yeah, I think we generally share a lot of blogs in our Halodoc blog platform, like whatever we do or whatever we build, right? So I request people to subscribe to our Halodoc blog platform to get us insights on what we do and what we basically implement at Halodoc. Yeah, if any questions, I'm happy to answer.
Jitendra, can you just go back to the slide where the architecture was shown?
Okay.
For platform 2.0.
Yeah.
Yeah. So actually, I want to know, like, I have two questions here. So first thing is, like, why do you have this raw layer of data after DMS? And the second is, what is the retention period that you are having in the raw layer? Like, is it forever, or you kind of archive that data somewhere, or how does that work actually?
Okay, sure. So the first question, right? We wanted to bring all the source data into one landing zone, right? So that anything we want to do kind of a processing that should connect to one particular source, right? So that is the answer for the first. So that landing zone for us for the EMR should be from the S3, right? So EMR should not connect to RDS, NoSQL database and all those. Second thing on the archival policy, right? We have not introduced currently the archival policy, but we are in the plan to introduce the archival policy. That's the correct point. Like, why do we need the raw data, right? Since the data is already available in the analytics tile. So this is going to have some kind of archival policy, might be a 1 week, 2 weeks, or a month, depends on the business use case, right? So mostly this data will be needed in the ingestion tile. Tomorrow, if some issue happen on the analytical tile and we are not able to identify at the beginning, ingestion tire will be very helpful to do the backfill of the data set. So that's the reason why we have this raw zone.
Okay, backfill in case of any errors if you are facing, right?
Correct.
Got it. Yeah. Okay.
Okay, I think I got some comments. So since this is a healthcare space, I assume there would have been requirements for access control. How did you go about it? If you can go over that requirement you have on a high level, and how did you go about it? Sure. So again, being in the healthcare domain, right, access to data pattern is very critical, right? So we have introduced lake formations in our platform, right? So that is provided by the AWS. So any data that is being accessed to this analytical trial, someone will be granted via lake formation, right? And how lake formation works is you register the glue catalog in the lake formation and you provide access to particular users on what all tables, what all columns they should have access to it, right? That is something related to the Lakehouse. Talking about the Redshift, we have a role-based access control that is being provided within the Redshift itself. So these are the two things currently we hold to grant access to our user. Again, I have not mentioned a very detailed view of the architectures over here. Might be in the AWS Asean Summit, right? You will be able to see a very detailed view of data governance, monitoring, alerting, how our workflow orchestration works and everything.
So Jitendra, how are you querying the data? Is it only through Athena?
Currently, it has support from Athena also and the Spark also.
When you say Spark, you mean Spark on EMR?
Correct. Spark on EMR using Spark SQL, or it can be a data frame or the data set.
But I'm wondering, like, since you mentioned lake formation, right? As of now, I don't think like we have integrated like the lake formation aspect, like how EMR works with lake formation. That is not quite integrated with Hudi, you know?
Yes.
I'm just wondering like how you are saying that you integrated with lake formation in that case.
I think lake formation is integrated only with the glue data catalog. That is true. With EMR, right, the control has been governed from the S3 IAM policy. So EMR is mostly used by our, let's say, data scientists, right? If they wanted to do some kind of if they wanted to build some kind of a model or the ad hoc analysis, then they can directly read the S3. But that is being currently governed by the S3 IAM policy.
Okay.
Yeah,
okay.
Currently I do understand a lake formation does not provide a lot of features, right? And that is where we are also interested to see, like, as you mentioned, right, integrated with the Redshift, integrated with the EMR and all those. I think what AWS mentioned is they have in the roadmap, like where they can bring lake formation as a centralized data governance tool. But currently we are finding a workaround to do all those.
No, yeah, I mean, because the lake formation that's integrated with EMR right now, that doesn't quite support Hudi as of now. We are working on that support.
I think it's not about Hudi, right? Lake formation connects to the Glue catalog, right, directly.
It connects to
Because
the
Glue
Glue
is just a-
catalog, but internally, like, I mean, the way the design is implemented, right? I don't know if you're aware of the record server, those components which are part of lake formation. Like, are you able to enforce like this these lake formation policies in your queries when you run on EMR? Do they like come into effect?
No,
With the
currently no.
policies that you have applied in Glue catalog?
Currently no.
No.
No. So let me try to reiterate this, right? Lake formation connects to the Glue catalog. So whatever tables you have registered to the Glue catalog, and if anyone wanted to access this data set with the help of Glue catalog, that will be governed by the lake formation, right? If anyone wanted to access data from the Hudi dataset, like you can also access the Hudi dataset directly from the S3, right? Since it's an open file format. That is where the S3 IAM policy is being introduced for us. So we are also waiting for the features like where lake formation can be utilized with the EMR also. But currently that is not the case.
Interesting. Okay.
Hey, Jitendra, I have a question. Can you briefly talk about what sort of delete use cases you have and how do you handle that?
Okay, so currently we don't have any kind of a delete use case being introduced in this platform. So what DMS does us, right, for us, if anything that is deleted in the source, it gives us the keyword that can help us to identify the delete statement. So tomorrow, if you want to build, right, again, this also, this capability we will bring like once the GDPR kind of a compliance comes in play, right? So currently we are not in that place. So once that is being implemented, we'll have these features also integrated with our platform. So that is one good point, like which Apache Hudi supports a soft delete or the hard delete on the dataset.
Okay, thanks. Any other questions, folks?
Maybe one question on your diagram for the architecture feed builder as well.
Yeah.
You mentioned having an analytics tier here that you use with EMR, and then you also go to Redshift as well. Can you talk about the differences in the use cases between the analytics tier with EMR versus Redshift?
Okay. So I think analytics tier currently holds the raw data, the basically behavior of the raw layer, right? So if it is a mutable, then S3 analytics layer holds that mutable behavior also, right? As I said earlier, our older platform, right, all the dashboarding and the reporting has been done on the Redshift. So bringing all those requirements directly to Lakehouse or the S3 layer, right, required a lot of changes and a lot of learning curves also.
Yeah.
So that's where what we did is we took a hybrid approach. We have a Lakehouse which mostly hold a raw data that is being available in the S3 analytics. I will not say raw data, but it's kind of a processed data. Some minor processing has been done. In the Redshift, we are following the data modeling concepts, right? Dimensions and the fact we identified like what data is required for our analytics, right? So based on that, we have categorized our data into different dimensions and the fact. Once the dimension and the fact is identified, we also understand what are the reporting use case they have, right? On an hourly basis, daily basis, or the weekly basis. So we aggregate the data and provide them the materialized view kind of a data to them, right? So this is the current approach. What is our roadmap down the line looks like is whatever workload we are currently supporting with Redshift, right? Everything will be pushed down to the Lakehouse. That is with the S3, and that is where the Lakehouse comes in play, right? So this is the basically hybrid approach we have taken, and over a period of time, right, you will see Redshift will not be there in our architectures, and everything will be supported with the with Apache Hudi or might be with the S3 layer.
Nice. Cool. Thanks for explaining. Makes sense.
All right. If we don't have any other questions, or we can take more questions maybe towards the end. Jitendra is going to be available.
Sure. Thanks, Sudha, I think, for giving this opportunity. So if anyone have any questions, right, might be we can talk offline over LinkedIn or anywhere. Thanks.
All right. Thanks, Jitendra. This was like really insightful. I hope all of us have useful, valuable lessons from your data lake journey.
Sure.
Right. Vinoth, do you want to take over?
Yes, yeah, thanks, Sudha. Yeah, hi folks. I'm here to talk about BigQuery Sync, the integration between BigQuery and Apache Hudi. I'm a software engineer at Uber. Yeah, next slide, please. So this is what we are going to see today. So I'm going to talk about some background and some motivation on why we built this. And I'm going to briefly touch upon Walmart's use case. This is from John, who is on the call. He's working at Walmart, and he helped me solve some of the problems in this use case. And I'm going to talk about implementation and high-level design of the BigQuery Sync. Then I'll discuss about how to use it and end with demo and some limitations. Next slide, please. So as you all know, BigQuery is one of the Google's cloud fully managed petabyte scale analytics data warehouse. BigQuery currently doesn't support Apache Hudi, but it has supports for Parquet, ORC, and Avro formats as external tables. Directly querying Hudi copy on write table on BigQuery results in duplicate records. At Uber, Uber is predominantly running on HDFS, on on-prem data infrastructure. But there are some use cases which needs to use Google's AutoML features and tensor-based processing for running some of the machine learning pipelines. For that, we need to load the data into Google's BigQuery for it to process. Similarly, when we do Google's ads data exploration, we need to join with multiple Hudi datasets to get some insights. And that was the motivation for Hudi. In Hudi, even before this BigQuery Sync, they were actually copying the data to BigQuery. So what happens is you compute the data, you store the data in HDFS, and then you copy the data, and then you run some ETL processing on top of that to make sure that the data is available in BigQuery. Normally, typically, the whatever is the latency offered by the HDFS, they will add 24 hours to it, and then you will get the data. So users were complaining that the data latency is not sufficient for them to process or do analysis on BigQuery. And that's the reason this is much needed for Uber, where it reduces the latency for those data sets. And even for Walmart, I'm going to talk about that. They have some critical use cases which are unlocked using this BigQuery Sync. Next slide, please. This is shared by Joyan from Walmart. I'm just presenting on behalf of him. Walmart is predominantly a Google Cloud Workshop where it leverages the compute and storage provided by GCP. Furthermore, Walmart runs most of the data intensive processing using BigQuery, so it can get practical insights in real time. And BigQuery also has a huge impact on the business with a 23% improvement over the processing time and much better user experience. For them, one of the most common use cases is where ETL pipeline extracts the data from multiple sources and in batch and streaming mode and syncs them using Hudi. So on those use cases, they need a separate ETL job similar to Uber, where they have using Spark's BigQuery connector. They copy all the data to Google's storage bucket for BigQuery, which involves an additional hop, and it adds additional cost and latency to the data as well. So this BigQuery connector is going to solve the problems for hundreds of thousands of pipelines, which will result in cost savings and access to fresher data. Next slide, please. So the implementation, high-level implementation goes like this. So Hudi maintains multiple versions of Parquet files, and it tracks the latest versions using Hudi's metadata. Since BigQuery doesn't support Apache Hudi natively, so without the metadata layer, when you sync the Parquet files to Parquet or ORC files to BigQuery, you will end up with duplicate records because Hudi maintains multiple versions of the Parquet files. To avoid the above scenario, the proposal is to implement a BigQuery sync tool, which will use Hudi's metadata layer to identify which files are the latest snapshot files and filters them so that when you query the table using BigQuery, you get the records with deduplication. You get to see only the latest snapshot versions and not the older versions. And this is performed for each and every commit file. So the sync implementation will identify which are the latest files for each commit and keeps those manifests synced with BigQuery as manifest table, so that you anytime you query the BigQuery table, you will see only the latest records. And this feature is implemented using the abstract sync tool, which is similar to the Hive sync tool, where whenever you update the data in HDFS and the Hive sync tool is going to sync the data to HMS. Similarly, whenever you when you write the data to Google's bucket, Google storage, you can use BigQuery sync tool, which will sync the metadata to BigQuery so that you see only the latest records. Next slide, please. On the high-level design, this is integrated with Hudi Writer, both with Spark Data Source, Delta Streamer, and Write Client, RDD Write Client. So whenever you write using these, whenever you have enabled the BigQuery sync configs, Hudi configs, when you write the data into a GCS, then after the write process is complete, then the sync process starts. The sync process creates 3 different tables in BigQuery. The first table being the manifest table. So when the sync starts, it calls the manifest utility, which is going to generate, it is going to query the latest snapshot files for each commit, and it is going to update that in Hudi's metadata layer as a CSV file. And on top of it, we create a table called Hudi manifest file. It is going to just have the list of latest snapshot files at all time. And the Hudi versions table is actually a table, external table built on top of the Hudi's files, all the Parquet files. So when you, this is the one which has multiple versions. So when you query this table, you will see multiple versions, so which will have duplicates. So to solve the problem, we have a Hudi table as a view, which is going to use the manifest table to filter out what versions of the files are latest in the versions table, so that when you query the Hudi table as a view, you'll see only the latest records. Next slide, please. So how to use this? For this, we created a GCP bundle, a GCP package in Hudi, which is going to accept some of the GCP configs. The top configs are like self-explanatory, where you have the dataset location, what geographic location that your data is located, and what is the project, and the dataset in which you are going to create all your BigQuery tables. And the table name for this is a table specific config. So you have the table name. This is the same as the Hudi table name. And then some paths where the base path is the table base path, and source URI is the URI used for BigQuery to query the data sets. And URI prefixes for partitioning. It gets the partitioning layout based on this prefix. And what is the partition field? Here it is date string, so it's DT. And here a bunch of other fields, which is going to help you sync the BigQuery. The data source, write, drop partition columns. So BigQuery doesn't require the partition column to be in the Parquet. So that's the reason we need to drop the Parquet columns. So for that, we have this flag. And BigQuery external table, not only Hudi, BigQuery in general has a limitation to support only Hive-style partitioning. So in order to enable Hive-style partitioning, you have this config. So once for a regular, any Hudi job, if you have these configs enabled, then automatically it uses the BigQuery sync tool to sync the data to BigQuery. Along with when you're syncing to multiple different data catalogs, you can sync with Hive sync as well as with for your internal queries, as well as with BigQuery for BigQuery integration. Can I get a control to share?
So you can make transfer, I think, or let me know if I want to.
Sure.
Okay, all right, hang on. Let me just reclaim and then give it back to you.
Okay, sounds good.
Thank you.
Right.
Yes, thank you. Okay. Okay, so what I have here is the Hudi as a Docker. I'm running on my local. You can also run on your local or like on your HDFS cluster, or which is writing to GCP, or on Google's Dataproc. The setup I have here for demo is the Docker setup. So the Docker is going to create all these nodes when you run this setup. Once you have that, then I'm going to generate some messages in Kafka, and I just did that. And to verify that, you just need to check. So here you can see that I'm publishing some messages on the topic stock ticks. And I'm going to get into the Docker. So here I have the properties file, which is I'm going to use for Delta Streamer job. I'm going to run a Delta Streamer job, which is going to read the messages from Kafka and sync them to a cloud store. Okay, here, this is the bucket I'm going to use for syncing the data. As you can see, I don't have stock text table here. And in the BigQuery, I don't have any tables here. Press that and check. So this detail-rich data set has no tables. I'm going to run the Delta Streamer job. So here, as you can see, I'm doing a Spark submit with Delta Streamer class. I'm passing the Hudi utilities bundle. Along with that, I have the Hudi GCP bundle jar, which is going to have the Hudi BigQuery sync classes. Along with that, I have the package for Google's cloud connector. The reason I need the packages, I have not built the Hudi GCP jar with dependencies. That's the reason I'm supplying this as an external dependency. And I'm going to create a copy on write table with Kafka source, and the target table is going to be on the cloud storage with Google with the base name as topics copy on write, and the target table is going to be copy on write. So I'm going to use the same Kafka source properties. I just publish that into HDFS as well. And finally, I'm enabling the sync. I'm saying the sync tool classes as BigQuery sync tool. This is the new implementation. Based on this only, it's going to sync the data to BigQuery. And it's just running the Delta Streamer job, where it is going to query the data from this topic. and it is going to create a table. It's reading the data from Kafka. I have some around 200 rows in that topics, and it just says that the metadata table was not found since I have enabled the metadata lookup. That's the reason it is looking for that, and it is log for that. Just in a few seconds, it's going to complete the job, and then you can see the data in the cloud storage. As you can see, you have a new folder. It has a bunch of dates and .hudi folder. Inside the .hudi folder, right now there is no manifest file. It is in a few seconds. Once it gets into that stage, you will see the manifest file as well inside the .hudi folder. Okay, you have the commit in progress. Okay, so now the commit got completed, then the sync started, and the sync is also complete. The job is complete. In the manifest folder, you see the latest snapshots, and if you go to the BigQuery, you will see 3 tables for this. Okay, you have the stock ticks copy on write view and the manifest file and versions file. I'm going to query the stock ticks.
Just a typo on there, you know, the feed. Oh yeah, you got it.
Yeah. So you see the data you have. Let me get the count. So since I have only one commit, that there are no duplicates. So you see only all the records. If I query the versions table, even that has the same, but I'm going to make one more commit. So when you make more and more commits, you are going to get multiple versions of the data. And then if you query the versions table, you'll see more and more records. But if you query the view, you'll see only the latest records. And if you query the manifest table, I'll just show you. So the manifest is just going to have the list of active latest snapshot Parquet files. Okay, there is another commit in flight. At the end of this, it is going to create more versions. Okay, I just completed the commit. And now if you query, you'll have after this commit, whatever is the latest Parquet fields, you have that. And when you query the versions table now, you have more records, 788, which of which whatever is from the latest commits duplicates, or the older versions are duplicates. But if you query the same view, you still have 591 records, which are non-duplicate, deduplicate records. That's all I have for demo. I'll continue the presentation. One second. Okay. So there are a few limitations. Currently, we support only copy on write table. But there is also works to support other table types. And the schema evolution is manual. Right now, if you're adding, if you're evolving your schema, you need to add the new columns, because the schema entrance works only the initially, like for the first time when there is no table, it first a schema, and then for future modifications, since these are external tables, if you delete the table and run the sync again, you'll get the new record, new columns as well, or you just add a new column to the BigQuery as well whenever you're adding a column to the payload. And the data must follow a default high partitioning layout. This is a limitation enforced by the BigQuery, and we haven't tested the data written using Flink, and that is something we need to productionize that code path. On the next steps, already some of the community members are working with BigQuery developers to support a custom input format. So when BigQuery supports custom input format, then you can natively add Hudi support. So then it will support all kinds of tables. And automatic schema evolution is just one PR away. Once we have that, then you can have whenever you evolve your schema, automatically that will be synced to BigQuery as well, and testing and productionizing the Flink code path. Big thanks to all the contributors. So Prashant from Uber's worked on. There is a Hudi manifest file, a Hudi metadata file, which is in non-Parquet format inside the partition folders that he worked on it to convert that into Parquet format, and Joanne worked on manifest creation code, and others from the PMC committers helped to land the code and fix the critical bugs. Yeah, that's all I have. Thank you, folks. Let's stop sharing now.
Thanks, Vinoth. That was very insightful. Do you have any folks? Do you have any questions for Vinoth? The BigQuery sync. I think we can open floor for any questions for both the presenters.
I have one for the room. Have people tried any yearly benchmarks on native versus Parquet tables? Like all of these anyway behave as Parquet tables, right? Now on BigQuery, like how's typically the external table performances in warehouses aren't as good as the native ones, right? Does anybody here have any experience signals around this?
We are in the process of capturing some stats, Vinoth, so from Walmart. So I can pass on the message and provide some stats in the slides and let you know in some ways.
In Uber, most of the tables are external tables, like Hudi tables. So we don't have a native BigQuery tables yet. Yeah.
I'm also curious because I'm sure you've seen the the capacitor blog, right? I think that's supposed to be Google's kind of successor to Dremel, and essentially like, you know, a Parquet++. So it'll be interesting to see, engine differences aside, if there are even file format differences there. It'll be like interesting to see.
Yeah.
Super cool demo, Vinoth.
Yeah. Thank you.
Any other questions or all right. I think we can wrap it up. I have just a thread open in the dev mail for timings for this community sync. Please chime in on that. If you have any preference over the timing, and we can discuss if a more suitable time would work for all of us. Thank you, folks. Thank you, Jitendra and Vinoth. See you all in the next month's community sync.
Thanks, everyone. Have a good day. Bye.
Thanks for the opportunity.
Bye-bye.